Hi, this is Professor Dorr, and this is lecture number 5 of EE 310. And in this lecture, we're going to discuss step response of series and parallel RLC circuits, which in our textbook, Alexander and Sadiku, is section 8.5 and 8.6. Now, we call this step response of series and parallel RLC circuits, and I kept that name because that's the name we use in the book. And of course, it's technically correct, but the way I like to think of the circuits we're going to work with today is at time equals infinity, there's going to be an energy source that's connected in the circuit. So you can see, for example, in this circuit that the switch is going to close at t equals 0, and at t equals infinity, this source is going to be connected to the circuit. So that's kind of how I like to think of the circuits we're going to work with today. So let's start off with this circuit. What's different from what we've worked on before? Well, we just kind of said that. We said that the voltage source is actually connected at t equals infinity. What's the final capacitor voltage? Let me just give you a second to figure that out. The final capacitor voltage at t equals infinity, let's see, we'll start off here with our voltage source, and we know our switch is closed, but I'm going to jump over here and I'm going to use my rule that tells me that there's no current in the capacitor at steady state. So no current here means no current here, no current here, no current here. So we'll use KVL on the fly that tells us we can start at Vs, go down 0 amps times R, so we're still at Vs, and we know that there is no voltage across an inductor at steady state, so I'm still at Vs. So the final capacitor voltage here is going to be whatever Vs is here. So in this case, we are applying energy to the circuit at t equals 0. And so what's the energy in the inductor at t equals infinity? Well, the energy in the inductor at t equals infinity will come from the current going through the inductor because, of course, the energy is stored in the magnetic field. And the energy is equal to 1/2 Li squared. So what's the energy in the inductor at t equals infinity? Well, at t equals infinity, this capacitor is going to block any DC current. So that means I got no current here, I got no current here, and that means I have no energy in the inductor at t equals infinity. What's the energy in the capacitor at t equals infinity? Well, let's see. We know that at t equals infinity, we have no current through the capacitor. So that means no current across here and no voltage across the inductor because there's no voltage across the inductor at steady state. And like we just determined, the steady state voltage here is going to be equal to Vs. So since we have a voltage of Vs, our energy in the capacitor is going to be 1/2 CV squared or 1/2 C times Vs squared. So bottom line for this circuit, at t equals infinity, I got no energy in my inductor, but I got energy in the capacitor. So here we see that we have a series RLC circuit. So now let's look at a parallel RLC circuit. So at t equals 0, I'm going to open this switch. So that means at t equals infinity, this source is part of the circuit. And of course, that's the different piece that we're dealing with today. So what's the energy in the inductor at t equals infinity? Well, at t equals infinity, I know that the inductor is going to have 0 volts across it. So that means there's 0 volts up on this path at t equals infinity. So that means I got no current here. And of course, I have no current through the capacitor at DC. So all this current is going through this inductor at t equals infinity. So the energy is 1/2 Li squared. Pretty cool. No voltage across the inductor, but a bunch of energy in it. Energy storage elements are fun. What's the energy in the capacitor at time t equals infinity? Well, we know that we have no voltage across here, so that means that I can't have any energy stored in the capacitor because there's no voltage across it. So the energy in the capacitor is going to be 0 at t equals infinity. So what we're going to do is we're going to update our equations. We're going to update them from the source-free case, like we had in the previous lectures, to equations when there is actually a source. But before we do that, let's just look at this circuit here. So at t greater than 0, V sub r is affected by 2 sources. Here's V sub r. I've got a source here. I've got a source here. So this voltage across the resistor is going to come from 2 sources. I've got this source and I've got this source. And so actually I should clarify that. The 2 sources that are going to affect the voltage in this resistor are the transient response from the initial voltage in the capacitor, because look at this switch, and it's a little different of a switch. At t equals 0, we're going to switch it from here over to here. So you can see at t equals 0 minus, we're going to get some initial voltage on the capacitor, and then when we switch our switch over here, that voltage is going to appear here. So one source for my voltage across the resistor is going to be the transient response from this initial voltage in the capacitor. And the second source of any voltage across that resistor will be this 15-volt supply. So we have 2 sources that are going to affect this voltage, or any voltage, or any current in the circuit. So if we have 2 sources, we'll use superposition. Hopefully you attended office hour several days ago where we used superposition to solve the first problem on the quiz. It wasn't the best way to do it, but we do it just because I wanted to reinforce the use of the superposition theorem. So the voltage across the resistor at time t is going to be equal to the voltage due to the transient, that's this up here, which dies out with time, and the response due to the steady state voltage due to the 15 volts. So let's look at the transient first. For the transient, the 15-volt supply is going to be disabled or set to 0. Now you notice that the characteristic equation is unchanged because the characteristic equation just describes the natural frequencies of the system, and they have nothing to do with how much energy it started with or how much energy it ended with, etc. Again, my copper pipe, the tone that it makes when I drop it will have the same frequency whether I drop it from up here or whether I drop here. Here I'll get boing, here I'll get boing, it's louder, but the natural frequencies are the same. So the characteristic equation is going to be independent of that supply. So let's take a look at what our equations are going to turn into. For the overdamped case, I'm going to have R of t, and remember I like to use R because it's the response of t, is equal to R sub s, which is the response due at steady state. R sub s comes from right here, plus the voltage due to the transient, which is going to be A1 e to the st plus A2 e to the st. Does this equation make sense to us? Well, what we found is that our s's are always negative, so this goes to 0 at time equals infinity, and this goes to 0 at time equals infinity. So R sub s is the response at time equals infinity. So it makes good sense. So it makes good sense. So now we go to our critically damped case where we have a little bit different of an equation, and it's the same kind of thing. Here we have e to the minus alpha t times all this stuff. This is the equation we worked with in the last few lectures. But we can see that as t goes to infinity, this is going to go to 0. So this whole term is going to go to 0. So R sub s is just going to be the response at time equals infinity. Let's move to the underdamped case. Again, I'm multiplying all the good boingy stuff here by e to the minus alpha t. As t goes to infinity, this whole term goes to infinity, and R sub t is going to be equal to R sub s. So what we can see here is that R sub s is pretty easy to get. It's just the response of the circuit at time equals infinity. Works for all three cases. So again, I use my R because I like to remind you that we're doing response, and it could be a voltage or it could be a current. If it's a voltage, it's one equation in the book, and if it's current, it's another equation in the book. So it could be any voltage or current in the circuit. And R sub s is the steady state. It's the t equals infinity value of the variable. So what we've been doing is to calculate our A1s and A2s here, we had to use all of our initial condition stuff to get us the response at 0 plus and the derivative of the response at 0 plus. Now we're going to raise the stakes a little bit and say now we also have to find the response at time equals infinity. So last lectures, all we needed was R of 0 plus and dr dt at 0 plus. Now we've changed it. We need R of 0 plus, we need dr dt at 0 plus, and we need R infinity. Now, before we go to practice problem 8.7 here, I want to give you a roadmap for solving these problems. This is not in the book, but I really like simple little comic book roadmaps that tell me where I'm going. You'll see that we'll have one also for Laplace transforms. We had my little timeline of t equals minus infinity and t equals 0 minus. And so I really like things like this. But the reason I drew this is I want to give you kind of a general procedure for solving these problems that'll make it hopefully a little easier for you. So here's the deal. We have a circuit up here, with its inductors and capacitors, and now it can have sources and stuff like that. And we are asked to solve for maybe a few things. R1 might be a voltage across a resistor. R2 might be the current through the inductor. You may have an R3, you may have an R4, you may have an R5. You may be asked for all kinds of different things. But what I want to point out with this roadmap is that regardless of what you're asked for, you got to recognize the topology of the circuit. Is it a series RLC? Is it a parallel RLC? Or is it what we're going to work with in the next lecture? Is it a general RLC? But for now, we're just doing series and parallel RLC. So regardless of what you're asked for here, find the topology of the circuit, because that's going to give you S1 and S2. Those are those natural frequencies. Those are the roots of the characteristic equation, because you're going to use those values of S1 and S2 for anything that you were asked for here. And that's kind of one of the big pieces of value of my little roadmap here is I want you to see, I want to separate out the natural response stuff from the specific response. I think in math they call that the particular solution or something, but I don't get too excited about that. So you can do either thing first. If you want, you can say I'm asked for R1 and I'm asked for R2, and for R1, I'm going to need R1 at 0 plus. I'm going to need DR1 at 0 plus, DRDT1 at 0 plus, and I'm going to need R1 at infinity. The infinity is what we just added in the last 10 minutes. And I know I need to get R2. So that means I need R2 of 0 plus, I need dR2 dt of 0 plus, and I'm going to need R2 of infinity. So I'm going to need these. I'm also going to need to deal with my topology to figure out which one it is, because in order to get S1 and S2, I need to know whether it's a series or a parallel or a general. Because remember, we have different equations. Remember, alpha is different for the series and parallel RC. So once I have my S1 and S2, I can get my response type. It's going to be overdamped, it's going to be underdamped, it's going to be critically damped, it's going to be a thud, it's going to be a boing, or it's going to be a thump. And I'm going to get these using my toadstools of alpha and omega naught. Remember, we said alpha is our thuddiness measurement and omega naught is our boinginess measure. If alpha is greater than omega naught, it's going to be overdamped. If it's alpha is less than omega naught, meaning the thuddiness is less than the boinginess, it's going to be underdamped. And if the two are equal, it's going to be critically damped. And what I get from this is the equation structure for R of t. It tells me whether it's going to be A1 e to the minus S1t plus A2 e to the minus S2t plus the response at infinity, or whether there's going to be sines and cosines in there. So I call this the natural response path. And this path applies to all the different specific solutions we're going to get. So that's why I bring it into the flow chart down here. So we were asked for R1 of t. Compute our specific, our initial conditions and final conditions for R1 of t. mix in the equation structure in S1 and S2 and compute A1, A2, you got R1T. And same thing for R2. Compute your particulars here for R2 and then throw the natural response in there. So, like I mentioned before, my little roadmap isn't in the book, but I think it's very useful. What I recommend to students is to print these things out and just tape it on your wall while you're doing problems, because every problem you do is going to follow this roadmap, and you can always tell where you are on the roadmap. And I really like that. You're going to have the same thing for Laplace transforms. Now, what we're going to do in the remaining examples in this lecture is I'm going to try to get cute with how I calculate things. Specifically, I'm going to have problems where I'm actually asked to calculate two different things. And what I'm going to do is try to make my life easier by saying, well, if I can get R1, it's related to R2 by just a derivative or something like that. So I'm going to try to work the problems that way, instead of saying, you know, I'm asked for two different things. Do this once, do this twice, and do them independently. So I know that sounds kind of confusing, but our general procedure is to, for the different things we're asked for, solve them all by themselves. What I'm going to play with in this lecture is taking one and using it to calculate the other. And we're going to kind of slog through these problems. And as we slog through them, I really want you to hang with me on these problems, because they'll really give you a good idea of how to do this stuff and how to do it different ways. And as I'm doing the problems, go back to the roadmap. Hopefully you've printed it out. You stopped the lecture and you printed it out, and make sure you know where we are on your roadmap. Okay, so we have a problem here, and we have two voltage sources, and I've got this switch that looks a little different than the other switches we've used, because at t equals 0, it goes from here over to here. In industry talk, we'd call this a single pole switch, because there's just one path going along the top here. It's single pole, but it's double throw, meaning it can go two different places. The switches we've used up to now are single pole, single throw. So that's just some good industry speak that'll hopefully help you on a job interview someday. Okay, we are asked for the capacitor voltage, and we are asked for the resistor voltage. So we're asked for two different things. If I go up here, I'm asked for the capacitor voltage and the resistor voltage. So let's triage the problem first. What I see here is a series RLC, because at t equals 0, my switch is connected over here, and the capacitor, the inductor, and the resistor are connected together. Ooh, I see a source in here that'll be engaged at t equals infinity, so that'll make it kind of fun. And let's see, I am asked for two different things. So our equations for R of t, the three equations that I always show, they're good for any voltage or current in the circuit. So I could just work the problem twice. Let's go over here. what I could do is deal with my topology, get my S1, my S2, my response type, and then apply it to VC and VR independently. That's one way I could do it. But I could also say, maybe I can save some time if I solve for VC first, and then I can get IC, which is also IR, because that is going to be just C dV dt. Let's look at the circuit while we do that. Let's say I get the capacitor voltage for time equals 0 plus. Well, if I have that, I can get the current through the capacitor by just taking a derivative, because I equals C dV dt. So by just taking a derivative of the voltage that I got the current. Same current here. I can multiply this by the resistance, and I get VR. So going up here, what I'm going to do is say, I was asked for two things, but I'm actually just going to solve for VC of t, and when I get it, I'm going to do a little bit of work on it, and then VR of t is going to pop out. So that's how I'm going to do this the first time here. And here it is. IC equals IR equals C dV dt. So VR is just going to be I times R, which is going to be R times C dV dt. That's the way we're going to do it. I'm going to make a statement here that says it's much easier to compute the derivative than to do the problem twice. Well, let's just see whether it is. And before you start worrying, because I can just hear the questions in office hour, Professor, are we going to be asked to make these kind of decisions on a quiz? No, I wouldn't do that to you. I wouldn't do that to me. But by slogging through this, you're going to get a much better feel for this stuff. But I don't want you to have to worry about whether you would have to make this strategic decision, because you may get it wrong. And if you got it wrong, you'd trash your quiz, and that's just not something I'm going to let you do. So I'm going to point you at the way I want you to do it on the quizzes. But let's slog through it, because I'm going to give you a much better feeling for this stuff. All right. So what let's do is let's start off by going down this path. And then we're going to get the equation structure out of it. So I know that it's a series RLC because I can see that. So I'm going to compute alpha. That's my thuddiness coefficient. I hope no respectable professors actually watch this lecture and see that I use words like thuddiness coefficients, but that kind of stuff really helps me. I like that intuitive stuff. So my thuddiness coefficient, and remember, alpha is different for the series and the parallel RLC. I crank the numbers and I get 2. And then I'm going to get my boinginess coefficient, or toadstool, omega naught, and that works out to be 4. And I can see that my circuit is more boingy than it is thuddy, or in other words, omega naught is greater than alpha. So it's underdamped, and I can hear that boing from here. This one's going to be a boinger. So I'm going to jump to the methodology that we used in I believe our second lecture. And I'm going to say, since it's underdamped, omega d, or in other words, another of our toadstools, is going to be root of omega naught squared minus alpha squared. And that's going to give me 3.46 radians per second. And what's the value of this omega t toadstool? It's the frequency that it's going to boing at. It's going to be the frequency that corresponds to the tone of my pipe when I drop it. Boing! See the exponential decay? Boing! But the that is omega d. That's the frequency where it's going to vibrate. So what have I done? I know my response type, and I know that it's underdamped. So I know, up we go to the roadmap, I know the equation structure. I know, and knowing the equation structure, I can use that to get my A1s and A2s. But I haven't done this yet. So let's do this now for VC. So the things I need are going to be my initial conditions, VC of 0 plus, and dVC of 0 plus, dV dt of 0 plus, and the new thing for today's lecture, VC of infinity. So VC of 0 plus, well, that's going to be equal to VC of 0 minus. Let's just look at the circuit and figure out what it is. So at time 0 minus, the switch is over here, and it's been here for a long time. And so that means that I'm in steady state, so I have no current through the capacitor, so it looks like I just have a voltage divider here. So VC of 0 minus is going to just be 2 divided by 1 plus 2, that's 2/3, times 18 is going to be 12 volts. Let's see if I got it right. Hey, look at that. Okay, now I need dVC dt. And we're immediately going to say that because of our basic equation for the capacitor, what we really need is the current in the capacitor at t equals 0 plus. So it's just going to be IC at 0 plus divided by C. So let's figure out what IC of 0 plus is going to be. And we're going to do it just by looking at the circuit. And I'm going to look at this inductor. And I know that at t equals 0 minus, I have my 15 volt source. Ooh, I got no current in the inductor at t equals 0 minus because this thing is open. So using my rule, I know I'm going to have no current in the inductor at t equals 0 plus. This switch is going to be over here at 0 plus. I got no current here. I got no current here. See that? I had no current through the inductor at t equals 0 minus. So that means I'm going to have no current in the inductor at 0 plus. Since the inductor is in series with the capacitor, I'm going to have no current in the capacitor at t equals 0 plus. So here we go. I sub L at 0 plus is I sub L at 0 minus, which is 0, so IC at 0 plus is 0. So dVC dt is going to be IC at 0 plus divided by C, just like we had here. It's going to be 0 over C is going to be 0 volts per second. Slap my hand, I didn't put units on here, but I should have. So I know that VC at 0 plus is 12 volts. We just got that up here. dVC dt at 0 plus is 0. VC of infinity, the third thing I need, what's that going to be? So at time equals infinity, this switch is over here, and I know I have no current through the capacitor because I'm at steady state. So that means I have no current in the inductor and I have no current in the resistor. So let's use Ohm's law and the rules to figure out what the capacitor voltage at t equals infinity is. Start at 15. Go down 10 ohms times 0 amps, and I have 15. My rule says there's no voltage across an inductor at steady state, so now I'm 15 here. So my capacitor voltage at time equals infinity is going to be 15 volts. And here we go, and that's the why. So now, let's look at where I am. I did all this stuff. I know my equation structure, and my equation structure is going to tell me how to compute A1 and A2. I dealt with all my initial conditions and final conditions, so I've done all this stuff. So now I got to compute A1 and A2. So we can use equation 849, or we can use the equations on sheet 2. And I know that V sub t is going to be, because this is underdamped, V sub s plus A1 cosine plus A2 sine. And we can see our Boyne frequency in here, omega d. Remember, it's the bung frequency. We'll substitute 0 in. This becomes 0. This becomes A1. This becomes 1. And V at 0 is just V sub s plus A1. So what you can see from that is I can get A1 really easily. Let's do it right down here. A1 is equal to V0 minus Vs. We have both of those. It's 12 minus 15 gives us -3. And now, going back to lecture 3, here's my formula for dV dt. Solve that for A2, and I have A2 as a function of a bunch of stuff we already know. We calculated this with our initial conditions. We just got A1 right up here. We have alpha, we have omega d. We put all that stuff in here, and we get minus 1.732. We shove all that into our equation, and here is our result. So now, let's go back to our strategy. We have Vc of t. We have Vc of t, but we're asked for Vc of t and Vr of t. And we're going to be clever. We're going to say, and that's right in our strategy here, if I solve for Vc first, I can get IC, which is also the same as the current in the resistor, which is C dVc dt, right? The capacitor current is the same as the resistor current. It's even defined the same way, isn't it? So that means VR is just going to be I times R, or here's my R times C dV dt. So what we're going to do is we're going to get the derivative of Vc and multiply it by RC. Again, going back to the roadmap, we got Vc. Now we're just going to doctor it up a little bit to get VR. And here's the formula we're going to use. VR is just C dV dt times R. We got to take the derivative of this. And that's going to be messy, so I'm going to use letters instead of numbers. Here it is with all our letters, and now we're going to take our derivative, and you can see we got to use the chain rule because we got two things that have t's in them, right? And so here's the first one, and here's the second term, and now we're going to gather up our like terms, and then we're going to substitute in our A1s, our A2s, our omega Ds, and this is going to give us 0, and this substitution is going to give us 13.86, and VR is going to be RC times our dVc dt, which this turned into this, and here is VR. So is this reasonable? Let's look at VR. Let's see, at time equals 0, this sign is going to be a 0, so there's going to be no voltage across that resistor. Let's go up to the circuit. Time equals 0, remember I'm going to have no initial current in the inductor at t equals 0 minus. That means no current in the inductor at t equals 0 plus. No current, no voltage. So I like that result. How about VR of infinity? Let's compare that to the circuit. My equation says that my sine wave is going to just keep on boinging along till infinity, but my exponential envelope is going to drive it to 0. So I'm going to say there's going to be no voltage across that resistor at time equals infinity. Well, at time equals infinity, the capacitor is going to prevent any current flow. So I'm again going to have no current through the resistor, so it's going to be 0. Now, before we answer our last question, let's do a little more checking. Here is our equation for the capacitor voltage as a function of time. Let's see if it's reasonable. At t equals 0, I'm going to say that at 0, this is going to turn into a 1. This is going to be a 0. This is going to be, my cosine is going to be a 1. So I'm going to get 15 minus 3 is 12 volts at time equals 0. At time equals 0 minus, we had a voltage divider that gave us 12 volts. Can't change the voltage across the capacitor quickly, so that means we're going to have 12 volts across the capacitor at t equals 0 plus, so our equation was good. What's our voltage across this capacitor at t equals infinity? Well, at t equals infinity, we have no current through the capacitor, so let's use KVL on the fly to figure out the voltage here. Remember, this switch is closed. Start at 15, go down 0 amps times 10 ohms. That means I got 15 here. Now we remember that we have no voltage across the inductor at steady states. That means I'm 15 here. So when I go back and look at my equation, it better give me 15 volts across that capacitor at t equals infinity. At t equals infinity, I'm 15 plus, at infinity, this e to the minus 2t is going to go to 0, so this whole mess is going to go to 0. Vc of infinity, 15 volts. So I've checked my result, and it looks pretty good. Okay, so that was a lot of slogging, and now we're going to slog through another similar problem. Actually, I'm sorry, before we do that, was our strategy good? Should we have done it the way we did it? Let's go back and look. What we chose to do was we were asked for two things, VC and VR. And what we did is we said, we're going to be clever. We're just going to solve for VC, and then we're going to take that derivative, and VR is going to fall out of it. What if we didn't do that? If we didn't do that, we would have said, okay, let's just compute we'll compute VR at 0 plus, dr dt at 0 plus, and VR at infinity, and then just apply this stuff to what we got here and just do it twice. I'm going to say that our decision was not really a good one because we had to take that nasty derivative of this sinusoidal term and use the chain rule. I think it would have been easier to have just calculated the initial conditions for the voltage across R. And I encourage you, go back and do that. Stop the lecture and go back and do it that way. Or in other words, get VR at t equals 0, dVR dt at 0 plus, and VR at infinity. So try it that way, and you better get the same answer that we have right here. Okay, this is a long lecture. I encourage you to take a break, go get a cup of coffee, go eat a banana, get a glass of water, go pee, let your brain cool off a little bit, and we'll come back and hit this example here. Next, we're going to work with this circuit here. And I want to know what the topology of this circuit is. And I kind of have to look at it carefully. I can see that my switch is going to close at t equals 0. And that means that I'm going to have an inductor. I can see it's in parallel with a capacitor, so I know it's not going to be a series RLC. But then I also see it's in parallel with not one resistor, but two resistors. And before we talk more about the two resistors, let's just look at this voltage supply here. It is 30 U of minus T. If it was U of T, it would turn on at T equals 0. But since we have a negative T there, of course, it's going to turn off at T equals 0. So at T equals 0, this is going to look like a short circuit. If you're uncomfortable with that negative T and why it turns off instead of turns on, just go back to the basic definition of the unit step function and you'll see it. So what we've determined is that at T equals 0 plus, I have a parallel R, and the two R's are going to be in series, so it's going to be 10 ohms, L and C. Okay, so it's parallel RLC, and we're asked for I sub L of T, there it is, and we're also asked for IR of T. And what I can see is that I'm asked for the current through this resistor. But when I am analyzing the dynamic characteristics of the circuit, those dynamic characteristics are going to be determined by this resistor in parallel with this resistor. So the resistor that I'm going to use for my alpha when I calculate that is going to be 10 ohms. But then I'm going to make sure at the end of the problem that I get the current through this 20 ohm resistor. Now, in our last problem, what we did is we were asked for two things. And so we calculated one, and once we got it, we kind of did some operations. Specifically, we took a derivative and got the other thing. But that was kind of messy. So this time, we're asked for two things. We're asked for a resistor current and an inductor current. So one of them is, we'll call it response 1, the other is response 2. So our strategy for this problem is first we're going to determine the response type, and that'll tell us the equations we need to use. And then we're going to get the initial conditions and final conditions for the two quantities that were asked for. So we're going to do the natural response path once, but then we're going to do the initial condition path, we're going to do it twice. And you notice if I wanted to do what I did last time, I could solve for I sub L, and then I could get the resistor voltage is just going to be the same as the inductor voltage, which is L di dt. And so the resistor current would just be the resistor voltage divided by R. So I could do this by taking a derivative as we did last time. But that was nasty, so let's just do it twice. But I encourage you, it actually turns out on this problem it's pretty easy. I encourage you, go back and do this. Make sure you're good with this and you can do it. Okay, so we'll begin the problem by finding the natural response. Or in other words, we're going to go down this path, and we're going to get our equation structure, and then we'll go this path and combine them in to get the two responses. So alpha is going to be equal to 1 over 2 RC because it's a parallel RLC circuit. And you notice my R is 20 in parallel with 20. It's 10 ohms. And I get 6.25. Now I get omega naught. 1 over root LC is 2.5. Alpha is greater than omega naught, so it's more thuddy than it is boingy, so it's overdamped. So I'm going to get a thud. And so when I have a thud, I compute S1 and 2 using this equation, which we actually derived this in, I believe, lecture number 2 for the source-free series RLC circuit. But remember, it's applicable to all these circuits. So I substitute in my alpha and my omega naught, and I get my two values of S. So I have gone down this path. I figured out the topology. I figured out what my response type had to be. I calculated S1 and S2, and I know the equation structure. So now we're going to do these. So let's start off with I sub L. So the three things I need for I sub L are I need I sub L at 0 plus, I need I sub L at infinity, and I need dIL dt at 0 plus. So I sub L at 0 plus is going to be equal to I sub L of 0 minus. Let's figure out what it is. So at t equals 0 minus, my 4 amps, of course, is on because it's on all the time, and my switch is open. So I don't have any connection over to this part of the circuit. So I sub L is going to just be 4 amps. And that's going to be I sub L at t equals 0 minus and also 0 plus. While we're here, let's find I sub L at t equals infinity. So at t equals infinity, this voltage source is going to be 0, so it's going to be off. So effectively, this 20 ohms goes to ground, right? But the thing that I really am going to focus on here at t equals infinity is there's no voltage across this inductor. So if there's no voltage across the inductor, there's no voltage across the resistor, so there's no current here. There's no current through this resistor, and since we're steady state, there's no current through the capacitor. So at t equals infinity, all that 4 amps has to be going through the inductor. So we're going to say that I sub L infinity is also going to be 4 amps. And here it is. So now we need di dt for the inductor at t equals 0 plus. So our voltage source, U of minus t, it's going to look like 30 volts, and then it's going to go down to 0 volts at t equals 0. So at t equals 0 minus, let's figure out our voltage on the capacitor. And you might ask, why are we going to figure out the voltage on the capacitor? Because it is in parallel with the inductor, and we're going to be able to use V equals L di dt to get our inductor dV dt. So at t equals 0 minus, I am going to have, of course, there's no connection here, and I have no current through the capacitor, so I just have a voltage divider. So the voltage on the capacitor is just going to be 20 over 20 plus 20 is going to be 15 volts. So that means the voltage at the inductor at t equals 0 plus is going to be 15 volts. So since the voltage on the inductor at t equals 0 plus is 15 volts, di dt is V over L. It's going to be 15 over 20. It's going to be 0.75 amps per second. And I say, wonderful, I got the 3 things I need. I got I sub L, 3 things we need. I sub L at 0 plus, I sub L at infinity, and I sub L at, di sub L dt at time equals 0. So now I have, let's go back up to our roadmap. I did all this first, so I'm cool here. And now I've figured all this stuff out. So I'm right here where I can mix all these together and compute A1 and A2. So we know that alpha was greater than omega naught, so our circuit is overdamped. So the form of our response is going to be I sub t equals I sub s, which is the steady state at t equals infinity, plus a1 e to the s1t plus a2 e to the s2t. And I know what s1 and s2 are, so let's just shove them in there. Here's my 11.98 and my 0.52. And we can even do more. We know t equals infinity. We have 4 amps in the inductor. So if t is infinity, obviously this is 0 and this is 0. So I of infinity is going to be 4 amps. This is the only thing that can be non-zero, so I sub s is 4 amps. So we're going to do this a little bit the long way. We're going to substitute t equals 0 into our equation. So if t equals 0, my exponentials become 1s, and I have I of 0 is I sub s plus a1 plus a2. Here it is. And of course, I know I of 0 plus was 4, so I have one equation. Now let's get di dt. And it's easy to take the derivative here. S1 just comes down in front of the e, and I end up at 0 plus with My exponential's going to 1, and here's my second equation. So now I have two equations in two unknowns. And so here they are. I have my first one, and I have my second one. So I'm going to just throw those in into a matrix. Here's my first equation. Here's my first equation, and here is my second equation. Sorry about that. Throw those rascals into a matrix, and I get A1 and A2, and I substitute those in, and here is my result for I sub L. Is it reasonable? Well, we know that at t equals 0, I'm going to have 4 plus, looks like 1 minus 1, so I'm going to have 4 amps. If t equals infinity, then these are both going to be 0, and now I'm again going to have 4 amps, so that looks pretty good. If I wanted, I could take the derivative and make sure my di dt is right at 0 plus. But so here is our first result. What we did, we solved for I L of t. Now we're going to solve for the resistor current. I believe that's what we're asked for, so we're going to go down this path. And we're basically going to do the same thing. We're going to get all our initial conditions, and then we're going to mix them with our natural response and our known equation structure, and we're going to get A1, A2, and then we're going to get that answer. So we want I sub R of t. And of course, it's still a parallel RLC, so S1 and S2 are the same. It's still overdamped. And what I'm getting at right here is all this stuff still applies. That's all I'm saying. So I need to get my initial and final conditions. I need IR at 0 plus, dir dt at 0 plus, and I sub r at infinity. So here's our circuit here. Let's get IR at 0 plus. So let's see. At 0 minus, this is disconnected, and it looks like I'm going to have my current in this resistor is going to be the voltage at this resistor divided by 20. So that's going to be the capacitor voltage divided by 20. Or I can just use the voltage divider theorem and say, well, I can say that my capacitor voltage at time equals 0 plus and 0 minus is just going to be 30 times 20 plus, 30 times 20 divided by 20 plus 20. So we get our capacitor voltage, we divide it by 20, and that gives us IR of 0 plus. It's 0.75 amps. Now let's get I sub r at infinity, because that's easy. And it's going to be 0 because at time equals infinity, remember the switch is closed, and this inductor is going to keep the voltage at 0 all the way across this path. So if this voltage is 0, I got no current. Now we want to get dir dt. And dir dt is going to be 1 over r times dvr dt. And since VR is equal to VC, VR is equal to VC, it's really 1 over R times d VC dt. So I really need dVC dt. But to get that, I know that I really just need the current going into the capacitor at time equals 0, because I'm going to use my equation of I equals C dV dt. So I need IC at 0 plus divided by C. So let's look at how we're going to get that. VC at 0 plus is equal to VC at 0 minus is going to be 15 volts. So IC at 0 plus, in order to make that 15 volts, to keep that 15 volts, I got to put out enough current so that I can maintain that 15 volts. Sorry. So that means I need to put 15 volts across the parallel combination of these two resistors. Or IC at 0 plus is minus, because it's coming out of the capacitor, 15 volts divided by 20 in parallel with 20, 15 divided by 10 minus 1.5 amps. Reasonable sign? Let's be intuitive. We know we have 15 volts across the capacitor. Think of it like a current fountain, and the current is coming out like that and going into both of those capacitors. So yeah, it's going to obviously be going from bottom to top, but positive is defined as top to bottom from the passive sign convention. So I like this negative sign. I could also visualize this by just saying, let's put the other 20 over here, and now I'll combine them, and I just have the capacitor and 10 ohms. And 15 divided by 10 is going to be 1.5. So I could do it that way. Just another way of looking at it. So dVC dt is going to be IC over C is going to be minus 1.5 divided by C, which is 8 millifarads, is minus 187.5 volts per second. So now I know dV dt. So dir dt is just going to be 1 over R times dVr dt, which is the same as dVC dt. 1 over R times dVC dt gives me minus 9.375 amps per second. So I have the three things I need. And the reason I kind of wrote them down here is because it's telling me I'm right here on my roadmap. I just went through here and I'm living right here right now. Okay, so we know that I of R at 0 plus is going to be I sub s plus A1 plus A2, because we know the form of the equation, or A1 plus A2 is going to be IR minus I sub s. And so that gives me one equation, okay? Or in other words, A1 plus A2 is equal to 0.75. Now, dir dt, I know that also. And if I differentiate my general form with my S1 and S2 in place, I get my second equation. I slap those into a matrix. I get A1 and A2, and I put those into my equation form. So what we did here is we just went down this second path. Now, if we wanted, as we pointed out at the beginning of this problem, we could have just got I sub L, and then we could have computed a derivative to get I sub R. I encourage you to do that if you've got the time. So we chose to do this problem twice, or in other words, we did the right-hand side of the roadmap twice, instead of taking a derivative. Was that a good choice? In the first part of the problem, we computed our I sub L, and it had a nice exponential response. And taking that derivative would have been pretty easy. Looks like I did it. And it was pretty easy. In the first problem, we had to take a derivative of a bunch of sines and cosines using the chain rule. And as far as I'm concerned, it would have been easier to do the problem twice. Now remember, on an exam, I'm not going to ask you to make those kinds of decisions. I'm going to tell you exactly how to do it. So these problems were a bit on the sloggy side, but hopefully you've got the time to go through them and you'll pick up all the little pieces that we covered. Maybe do these problems different ways, maybe check your work in different ways. I'll see you at the next lecture, and I hope to see you in office hour.